So once again, it's the same setup as last class. Last class it was a 4-sided dice, so that when I was writing down all the formulas, I only had to add up 4 things. This class, it is a 6-sided dice, so there's going to be 6 possible outcomes when you do the calculations, but otherwise the same kind of problem. So you choose the number you want, y hat. Why is it called y hat? Well, we're thinking of the outcome of the dice roll as capital Y, and you are trying to guess what's going to be on the dice. That's the game. You want to try to predict the future and predict what will be on the dice. So predictions in this class have a hat. So y hat is your prediction. Capital Y is the actual outcome. And then you pay based on how far away you are. If you're very close, if you get it exactly right, you get to pay $0. If you're off by 1, you pay $1. If you're off by 2, you pay $4. You pay the square of the number of dollars. We're going to see why squares are nice for this kind of thing momentarily. But let us see what you guys chose. If you were paying attention last class, you know the perfectly best answer. Reveal counts. All right. So 19 people picked 3.5. 2 people picked 3. And now's the fun part. We get to roll a dice and see what the actual outcome is. Here, I'll roll it over here, and you can yell it out for everyone. What was it? It was a 1. So that means the people who picked 3 only owe $4. They were off by 2. But the people who picked 3.5, they owe $2.50 squared. That's like, what is that? $5 or something. $5.25. So does that mean 3 is the right answer because they paid less money than the 3.5? No. The right answer, as most people got, is indeed 3.5. So the problem with picking 3 is when the dice comes up 1, you owe a little bit less money. But when the dice comes up 6, which happens about as often as it comes up as 1, you owe even more money. So 3.5 is the balance point where you're sort of like managing the sort of worst case scenario. You're being fair to all the possible outcomes, whereas 3 is not as good as 3.5 because 3 is further away from the big numbers like 6. And it is a little bit confusing. Why should it be that the dice can only be an integer? Why is it okay to estimate not an integer? Well, first of all, I told you in the rules of the game that it was okay. But in this case, it is better because it is balancing better than just picking 3. So if you chose 3, that's the wrong answer. And you probably were like, oh, I have to pick an integer. In fact, you do not have to pick an integer. So when you have this kind of regression problem, try to get as close as you can. It's okay to sort of balance between 2 different outcomes. Okay, we're going to go deep into this problem in a minute. But any questions or comments so far about this problem with the 6-sided dice or the 4-sided dice from last time? Okay, so what we're going to do this class, if you remember last class, we proved it using a picture. In this class, we're going to do the clever proof that's also going to reveal some useful information. So this class, we're going to do the same problem 3 different levels. So these are the levels, and this is the level we're doing now is the no data level, and right. So and what we know exact sides of dice. So in the problem, I told you the dice has one side that says 1, one side that says 2. You could examine the dice and know exactly what it's doing. And we found that the best estimate, actually, I don't care about the best estimate. I care about the error. And the error, we will see, is the variance of the dice. That is what I claimed last class, and we'll prove this class. And we're going to see that the name of this error, or the lesson we're trying to learn here, is about irreducible error. And so this is the first lesson we are learning, is that even if you know the sides of the dice perfectly, when you're playing this game of trying to estimate a random number, you will never get it perfectly right. So if you pick 3.5, that is the best possible answer, and you will still owe money to the person playing this game with. And the name of this error has a fun name. It is called aleatoric. Aleatoric. And this word alea, this is Latin for dice. This is Latin for dice. So there's a famous quote by Julius Caesar who says, I don't know, should I speak Latin? Yeah, let's do it. Alia jacta est, which means I threw the dice. And so he did that. He was like about to start a war. So he's like, let's game on. Let's see what happens. For us, aleatoric error is error that is sort of due to the randomness of the problem. No matter how smart you are, no matter how carefully you examine the dice, no matter how carefully you do the problem, you will still pay money through this irreducible error. So we're going to see exactly why that is. We're going to do the proof today quite quickly. And then we're going to kind of upgrade to what happens if you don't know the exact values of the dice. So we're going to do the dice problem, but with samples. So we're going to have dice samples, and we're going to do exact sides are unknown. Okay, and then we're going to come back and fill in this table and see how does that affect the error, and we're going to learn we're going to learn something about the error, and then we're going to do the same thing, but we're going to do it with data. So in addition to having rolls of the dice, which are y values, these are y values, so observed, I'll call these observed y values. We're going to have actual data. This is our first problem. And I'm going to call this a one-dimensional data. We're going to have observed x and y values. Okay, so this is like the first baby data problem that we're going to do in this course. We're going to have some actual data. And then we're going to see how that affects the error and what this tells us about errors. Actually, maybe I will put in the main thing that we want to get to. The most important thing is this bias variance decomposition. And it was presented a little bit differently in the videos at a high level. So we're going to kind of do it from a mathematical side of things. And this is the idea of under versus overfitting. So that's what we want to get to. And we want to sort of understand this in the simple case of the one-dimensional problem. And then, most of the course is going to be multi-dimensional problem, looking at lots of different complicated things. But this under versus overfitting is always there, is always really important. That's why we want to do a simple mathematical example so we can build some intuition. If you kind of see this for the first time, it's very counterintuitive. I'm going to try to show you in this situation. Hopefully you'll build some intuition and you can carry that over to the harder problems. That is our goal for today. Okay, we're gonna start here. I'm gonna prove these things, the variance, and so on. But any questions or comments at this point about any of this stuff? So we're gonna do maybe half the class will not connect to the videos, and then we're gonna get to the videos when we get to this last little problem. Okay, let's start with this thing, and this was the claim I made last time, is that in the 1D in the dice problem, the best choice in the dice problem. The best choice is, what was the best choice? You guys all knew it, is y hat is the average value of the dice. And the loss function at this point, the loss function is the variance of y. So what this is saying is the best thing you can do in the warm-up problem for today is exactly what you did. Guess the average of the dice. For a 6-sided dice, it was 3.5. And the amount you will pay on average is the variance of that dice. Okay, and here's the proof. So last time we did the proof by writing out all the possibilities. And this time we're going to do the sneaky way. So using a trick. And the trick is called the Pythagorean theorem for random variables. Using Pythagoras for RVs. RVs are random variables. And that trick is going to let us do it. So we're going to write out the loss function. The loss function as a function of y hat. Maybe I should put a little star here. So the best possible thing is this much, because I just want to talk about a generic y hat now. So this is the average value of rolling the dice of y minus y hat squared. Right? So we were told in the game that this is how much you pay when you lose it. When you play the game, you lose y minus y hat squared dollars. So this is how much you lose, your loss function. And we're averaging over capital Y. Some people call this the test. This is some kind of theoretical test error. So Y is a test point. A test point. And we're saying, you made the choice, and then you see on a dice roll that you have not seen yet how much it is, and we're doing it on average. So this is really the average test error. So this whole thing altogether, this is the mean squared. Some people call this the mean squared error. So this is the theoretical test error. I'm going to say average, then that's the word I need. Theoretical average test error. Okay. This is all, I went kind of quickly. This is all review so far from last time. Questions or comments here? Is the setup clear? If the setup is not clear, we're gonna start hitting it with the sword. So it's going to be harder. But questions? Okay, let's keep going. So here is the trick. This is a mathematician's favorite trick, which is you add and subtract 0. Right? So I can take this thing and I can just rewrite it. This is equal to the expected value over y of y minus the expected value of y plus the expected value of y minus y hat squared. So first of all, you should believe me that these two things are equal. Why are these two things equal? I subtracted a number, and then I added the number back on. For the regular dice, I'm adding and subtracting 3.5. For the four-sided dice, I would be adding and subtracting 2.5. Whatever the mean of y is, I'm adding and subtracting it. So first of all, it's totally true. You can't argue with me about the truth of that statement. What you can argue with me about is why on earth would you do such a thing? This is a very silly thing to do. Have I changed the problem? Have I done anything useful? You might say no. Look, it was like that, it was like that. This one's more complicated. You made it worse. There were two hard things written on the board. Now there's 4 hard things written on the board. How is that any better? And the answer is, now we can use the Pythagorean theorem. And the Pythagorean theorem says, the regular Pythagorean theorem says if you have something A and you have something B and you try to measure the length of the sum, so if you do the vector A, let's make these vectors A plus B. So what does the regular Pythagorean theorem say? It says if you measure the length of A plus the length of B, that's the length of this diagonal vector AB, the length squared of A plus B is equal to the length squared of A plus the length squared of B. That's the regular Pythagorean theorem. And it only works if this is 90 degrees. So when A, B are perpendicular. Okay, that's the regular Pythagorean theorem. Does anyone know, how would you check if A and B are perpendicular, if they're vectors? How would you check? Like, what kind of thing would you do to check if they're perpendicular or not? You can look at the picture and see they're perpendicular here, but how would you do it? I have two, maybe you? Yeah.
The cross product should be 0.
Yeah, the cross product should be 0. A cross B equals 0. Is that what you were going to say as well?
So that kind of the converse of that. The dot product should be 1.
The dot product should be 1. Okay, A dot B equals 1. Okay, so maybe it's the cross product being 0. Maybe it's the dot product being 1. This is like your linear algebra class. Everybody take 30 seconds. Let's think. Actually, I'll open and mathematize. This is a good one. Which one of these is it? I'll let you guys think, and we'll vote. So take 1 minute. Feel free to talk to your neighbors. This is a great lesson on linear algebra, and it's going to come up in our thing. You're going to see exactly what the correspondence is. Okay, it is open in Mathematize. You should have 3 possible answers. The cross product is 0, the dot product is 1, or something else. And I will give you guys 30 seconds to put in your final answer here. Okay, put in your guesses. Time is almost up. I think we had 21 people on the first question, so hopefully we'll get 21 people this time. And let's see how these things are going. Okay, let's reveal what people said. Oh, okay. 13 people said A cross B equals 0. 4 people said A dot B equals 1. 6 people said something else. The correct answer is, it is something else. And in fact, the something else is a combination of these two things. So I think both people remembered half of the right kind of stuff. And if you combine these two answers, you get the correct something else. Does anyone know what the correct something else is? The cross product should be 1. So to combine these two things, you could combine them and say the cross product should be 1. That is not the right way to do it. There is another way you can combine these two things. The dot product should be 0. Amazing. Yes. Okay. So that's what it is. Very good. So there's a good little review. The right answer is that the dot product should be 0. Do I have an eraser? The dot product, A dot B, should be 0. So if you have two vectors and you know the dot product is 0, then you can use the Pythagorean theorem and know that the length squared of the sum is the individual sum of the lengths squared. So you can kind of pull the plus outside of the bracket and pull it outside and have A squared plus B squared. That is the Pythagorean theorem. Why is that like what we're doing here? The same exact thing works for expected values. In fact, expected values are kind of like a dot product. So this thing, it will be equal to the individual squares. So it'll be y minus expected value of y all squared on average, plus it'll be the expected value of the difference, expected value of y minus y hat squared, like that. So same kind of thing as before. You have a combination of two things squared, and you can write it as the sum of the individual squares. That's what the Pythagorean theorem is saying. As long as what? As long as, what do we need? We need the dot product to be 0. What is the dot product in this case? It's the expected value of the product. The expected value of the product, y minus expected value of y times expected value of y minus y hat equals 0. So whenever you have a product of two things who are on average 0, you can use this Pythagorean theorem. In probability, this kind of thing, when you have the product of two random variables that is 0, so that the expected value of A times B equals 0, this has a name, which is uncorrelated. Means A, B are uncorrelated. So in geometry class, you say perpendicular. In probability class, you say uncorrelated. And they mean the same thing. If two things are uncorrelated, then you can apply the Pythagorean theorem for random variables and split up the sum of the squares as the sum of the individual things squared. I will prove this in a second. It's not a hard proof. So proof coming soon. It's proof. Proof, TBA. We'll do the proof in a second. And now you can see, when I was saying why did I add and subtract the expected value of y, when you subtract the expected value of y minus the expected value of y is mean 0. So y is some random thing. It has an average of 3.5. But if I subtract off that 3.5, now the average is 0. And if you multiply it by a number, like 3.5 minus whatever your guess is, it will be 0. So I forced two things to be uncorrelated. That is why I did the step that I did early on up here. When I did this step of adding and subtracting to create these two things, I was doing it exactly so that this one would be mean 0. Okay. You guys with me so far? Questions? Okay. So we're very close. We now have a sum of two things. We just have to simplify it a bit. This one is, there's the random variable y, and we subtracted its mean, and we squared it. This thing has a name, and the name of this thing is the variance. That's the definition of the variance. So this part equals, it's going all the way down here. This is equal to the variance of y. That's the definition of the variance from our first class, or from probability class. Y minus its mean, all squared. How far away is y from its mean on average? Squared. That is the variance. And the second one, this is the average over y, but there is no capital Y anymore. This is the average of something that is always the same number, which is whatever estimate you did minus the expected value of y minus y hat squared. So this is the final result that we have gotten, is this nice formula. And it says that the loss function, even though it seems very complicated, actually can be written as a simple quadratic equation. It is how far away you are from the mean squared plus the variance. And we can check this. We had this graph on our board yesterday in Desmos, but we didn't have this formula. So let's check it and make sure that it works. So let's open back up Desmos, and let's do it for the four-sided dice. So for the four-sided dice, we had x minus 1 squared plus 1/4 x minus 2 squared plus 1/4 x minus 3 squared plus 1/4 x minus 4 squared. This is what we had on our last class, and this is how we knew the minimum was at 2.5, and we saw the minimum value was 1.25. All right. But on the other hand, if I make a number called v, that'll be the variance. Let's start the variance at 2.25, I believe is what it is. And the mean, we'll call that m. That's 2.5. And then I do x minus the mean squared plus the variance. That is that. Okay, what is the actual variance? I guess it's not supposed to be 2.25. It's supposed to be 1.25. Right, so we're moving this thing down. So if you calculate on a four-sided dice, the variance is 1.25, and the mean is 2.5. This formula is the same as that formula. And that is what we have proven. So we've decomposed by using the Pythagorean theorem to see a very simple formula of what is the square loss. It's just how far away you are from the mean squared plus this irreducible amount. And you can never go below this irreducible amount, right? Y equals v. That is the minimum value you will ever see in this thing. So that's the irreducible error. This is how much you actually pay. You want to go down to the minimum and get that irreducible amount. So this is another proof of what we did last class, of noticing that the minimum occurs exactly at the mean, and the minimum amount you will pay is that irreducible error of the variance. Okay, there it is in graph form, and in math form, we can just write maybe a couple things. Therefore, by basic quadratic equations, the minimum is at y hat star equals the expected value. So that's the minimum possible thing you could ever get. And the minimum possible value is exactly just this variance part, right? So when you're at the minimum, the second term is 0, and you're left with just this irreducible part. Okay. That is the proof. I'll prove the Pythagorean theorem in a second. It's actually very simple. But questions or comments about this idea? Yeah?
Can you scroll up a little bit real quick?
I absolutely can, yeah. In fact, let me zoom out so I can get a little bit more in case there's something else you're missing. Is that okay?
Yeah.
Okay. Anyone else? And by the way, so I do try to record these lectures. Sometimes it goes wrong. But if you watch the recording, you can always get the note. And if people want, I can also try to post them online. It's kind of annoying to always have to export them and post them, but I can try. If you want them, if you'd find it helpful, I'm happy to post them. Yeah, and like I said, I think the main way is to go watch the recording and then just like fast forward to the part where we did the thing that you wanted, and you can see what it is. Okay. Okay, let me prove the Pythagorean theorem. Very simple proof. So the expected value of a plus b squared, so this is claim, this is equal to the expected value of a squared plus the expected value of b squared. And then I'll say when the expected value of the product when they're uncorrelated, ab equals 0. Okay, here's the proof. The proof. All you do is expand things out. The expected value of what is the expected value of a plus b squared? That is the expected value of square the first term, square the last, double the product, maths a blast. There we go. Binomial theorem. And then the expected value is linear. You can always move this in to these other terms. So this is the expected value of a squared plus twice the expected value of ab plus the expected value of b squared. And this term equals 0 when the expected value of AB equals 0. So if someone tells you they're uncorrelated, this middle term just drops out, and you have exactly the result. A plus b squared is equal to a squared plus b squared. The middle term goes away under the assumption that they are uncorrelated. So I'll just leave it there. Okay. These two slashes mean I'm done. Okay. Questions or comments about that one? All right. Now that we've learned everything we can from the dice, where we know all the individual sides, this is all probability. Now we're going to move into statistics, where you don't know the sides of the dice. What do you know? You know something else. And that's going to be the next mathematized question. All the way up here. I call it data dice. So this time, you are not allowed to look at my dice beforehand. I'm not going to tell you that it has one side that has 1, 2, 3, 4, 5, 6. It's an unknown mystery dice. Some weirdo dice from this bag. You know, it's one of these weird, I have lots of dice here. I'm going to pick a weird dice. You don't get to see it. You don't get to know the number of sides, or if it has, integers written on it. You don't know anything about it. But what you do know is I will let you see the result of me rolling the dice. So you are going to n data times. So n data is the number of data points you have. We're going to roll the dice n data times, and you get to see the results. So you get to see y1, y2, all the way up to yn data. So you get to collect some data about the dice, and then you're going to use that to make the decision. So use the rolls, use y1, y2, y up to n data, to come up with an estimate for y hat. And I will emphasize, no cheating by assuming anything about the dice. You might assume the dice has 10 sides or less or something, or like it would be impossible for him to have a dice with 1,000 sides in his backpack. Don't assume that. It could be a 1,000-sided dice. It could be a 10,000-sided dice. The only thing that you can do is use these numbers and don't use any other assumptions. Then, once you have come up with your estimate of y hat, then it is the same game as before, where we're going to roll the dice one more time, and then you pay me according to how close your estimate is. And once again, you're trying to get as close to as possible to the true outcome. And just like before, you probably, depending on how you do this, you can do it better or worse. So what is the right way to do it? Is the setup clear on what you're doing and how it is different than what we did before? Okay, so what is the question I'm going to ask you to do? Think about this. So first of all, the hard part is how are you going to compute y hat, right? Before we had a strategy for computing y hat based on the sides of the dice. Now you don't have sides of the dice, you have data. How are you going to compute y hat? And then this is the question, which is, if you plotted how much you pay me versus the number of dice that are rolled, what does the graph look like? So presumably, it is, is it better or worse for me to roll? If I roll it one time, is that better or worse than 2 times, and so on? And choose which of these graphs. So the options are the blue graph, the green graph, the purple graph, or the red graph. Which one represents the amount of money you pay me as a function of how much data you have? So the number of dice rolled is the n data. That's what I want you to do. Is the question clear? Yeah, question in the back, yeah.
So, if we're taking an instance, when you roll the dice, whatever number of dice it is, the number that appears is our y, right?
Uh-huh.
So, what exactly is the n? You said fix a specific number, n.
Yes, so n, so I think you should think of it like
N, what we're guessing.
n is the number of data points you see. So you get to see, let's say I roll the dice 10 times, and then I give you the outcomes of the first 10 times I rolled it, right? And you're using the first 10 rolls to come up with your guess of what the next roll will be, right? So in the previous example we did, the warm-up problem and the problem we did last week, I didn't tell you anything about the dice, except where I said, look, it's got one side that's a 1, one side that's a 2, one side that's a 3, one side that's a 4. But now I'm saying, I rolled the dice and I got a 7, and then I rolled the dice and I got an 8, and then I rolled the dice and it was a 4. Like, I'm telling you the data, and you have to use the data to come up with your guess. And the question is, how does it look like as a function of your sample size? So when you have more dice rolled, how does the error change? That's the question. That's what we want to understand. Okay, this is a pretty in-depth one. Feel free to talk to your neighbors. I'll give you 2 or 3 minutes to think about this. Coming up with just how are you going to compute y hat is not easy. And then also, what does the graph look like? Also not easy. Think about what you think it could be, and hopefully we'll learn something. Okay. Okay, there's 30 seconds left, so put in whatever your best guess is as to which graph you think it is, and we'll discuss based on what you guys chose. Okay, just a couple more people to get in. A couple seconds left. Okay. Very exciting. Let's see what you said. I guess before we do this graph stuff, let's talk about what is the y hat. Does anyone have a formula that they like for y hat? So let's see. Before, when we were told what is on the dice, we said average the sides of the dice. And that is y hat equals expected value of y was the best. It was the best. But now you are not told the sides of the dice, so you cannot possibly compute the expected value of y. You have to do something that depends on y hat equals some combination of the data that you saw. And the data that you saw is these samples, y1 up to yn data. I'm actually going to put n equals n data up here and just write n everywhere on the blackboard to make it a little cleaner, but it is the number of data points. Did anyone have a formula on how they combined the y1 to yn that they thought was the right way to do it?
You can take the average of y1 to yn.
Yes, the average of y1 to yn. That's a very reasonable thing to do. Average of y1 to yn, and that in as a formula would be 1 over n times y1 plus dot 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 plus yn. Okay, and it is worth pointing out n is the number of data points, so n could be much larger than the number of sides of the dice. So this is a different calculation than this. This thing is sometimes called the theoretical average. The theoretical average. So the theoretical average of a dice is exactly 3.5. And this thing is called the empirical average. Empirical. Empirical means based on experiments. Empirical. And so it's not going to be exactly 3.5. Maybe you'll roll it. Let's do it 2 times. When n equals 2, I got a 6, and then I rolled it again, and I got a 3. So my empirical average is 6 plus 3 divided by 2 is 4.5. It's not exactly the same as this, and it depends on y1 to yn. That's a very good idea, kind of a natural idea. Let's use the empirical average instead of the theoretical average. Did anyone have any other ideas? Yeah.
Another way, I think we can also take the range and divide it by 2. So the greatest number will be got in the number of rows. Minus the smallest number, and then divide it by 2.
Yes. Okay. So you want to like put it in like bins and say like how many times was it the smallest number? How many times was it the next smallest number? Yes, this is a great idea. If somebody is in a physical room and like you what's the name of the bad guy from the Saw movies? Jigsaw, right? He captures you and puts you in a room and says, here's some tricky stuff about dice. What you're doing is exactly the right thing. However, I don't want to assume that they're dice. Like I want it to work for any random variable. And so in particular in real life, sometimes there is no largest value and there is no smallest value. So it could be very large with a small probability. So in real life, you don't want to do something like see how many times was it 1, right? How many times was it the largest value? Those are good ideas for actual dice, but I want to keep things more general. And I was trying to say that when I said don't assume anything about the dice. That's what I was getting at. So I don't want to do like bins or something else, which are great ideas that assume like the dice has a smallest value, but we're not going to make any of those assumptions. So that's a very good idea. Did anyone else have any other ideas? If you have a collection of numbers y1 to yn, what else could you do other than the empirical average? There's two more that if I went to an elementary school and I said, hey kids, tell me what you can do with these n numbers. They tell me the average, and then they tell me two other ones. What are the two other ones? Yeah.
Median and mode.
Median and mode, yeah. So this is another totally valid thing. You could do the median of y1 to yn, right? That's like the middle number, or you could do the mode of y1 to yn. And these are all great ways to estimate something about the data, right? You have n data points and you want to condense it down to one number. The average is away, the median is away, the mode is away. There's other much more complicated things. Like in real life, there's some situations you want to do something called the median of means, or the mean of medians, I think is the one they use. The mean of medians. In the mean of medians, you divide it into groups, and then you do the median of each group, and then you take the mean of the medians. There's some weird situation where you want to do that. And all of these things, there are situations where you want to do them. I'll tell you one that's an easy one. The mode will be this will be correct the most often. So the mode is the number that is the correct the most often. So if Jigsaw ties you in the room and says, I'm going to kill you unless you get it exactly right, then you want to go with the mode. But if Jigsaw says you have to pay me dollars equal to how far away you are squared, then it turns out the mean is the best one. So these ones are good for other loss functions. These are good for other loss functions. And it is true that this one is the best for the square loss. And the proof is not too complicated, but I'm not going to go into the details of exactly why. It is basically the thing we saw before of this kind of thing, right? The square loss has this square feeling to it, and it's like how far away you are from the mean squared, and all these things. So the best one you can do is this thing. Okay, so very nice. That's the estimate we're going to use. This is called the mean estimator. We're estimating the theoretical mean by using the empirical mean. Very nice thing you learn in stats class. Questions or comments about this stuff? Okay, now let's go back to the question I was asking you before, which is what I really want to discuss, which is what does the graph look like? And your options were red, blue, green, or purple. And I'm just curious to see what you guys said. So let's look at it. Reveal counts. Okay, here we go. So let's talk about blue, green, and purple, and red. Red seems to be the most common. Green is a bit of a wild card, because green is the only one that goes down for a while, and then it goes up, right? So if you chose the difference between green and the other ones, is you're answering the question, is more data better? Right? If more data is always better, then the more dice we roll, the better we'll do, the less loss we will have. But if you chose green, you sometimes think, hey, you should stop after a certain amount. And only 3 people picked, 5 people picked green. Okay, very good. So green was actually the second most common choice. So let's address this as a sort of philosophical question here. Question. Is more data ever worse? And if you think the answer is yes, then you should choose the green curve. And if you think the answer is no, then it's going to be one of the other ones. Does anyone want to take a stab at this one? Or how they thought about it? Maybe somebody who picked green. Why did you pick green?
I think after a certain point it is because it takes you away from the true value, because there are multiple data points involved. So it takes you from the true actual value of the data. So there is variance.
Yeah, I think so. You're getting at a very important idea. And indeed, if you watch the videos, the idea I think you're talking about is in those videos, which is you can sort of go too far. And you can go too far. So this is the idea. The idea sometimes in data science, you can go too far. And indeed, this is a really important idea. And we are going to get to this idea. But this idea does not apply to the data. So this idea, this will be for something else. This will apply. This is a really $1 million brilliant idea. But it is this idea that goes with a different question. So not with this question. So the too far here, we're going to see what that is. And in fact, is more data ever worse? If more data was worse, you could you figure out how much is the optimal amount of data, and then you could delete the new data, right? So if you were smart enough and more data was worse, you could just delete some of the data. You're allowed to do that. You can say my y1 to yn, step 1, delete all the data past n equals 10, then do whatever you were going to do. So is more data ever worse? And I'm going to put the answer is, I'm going to say all else being equal, no. So more data is always better as long as everything else is equal. We're going to see this idea, you can go too far, and that's going to be a situation where all else is not equal. We're going to see that, hopefully by the end of today's class. So the green one is not the right one. The green one is not the right one. Okay, if the green one is not the right one, then what do the purple and the blue have in common? The purple and the blue versus the red. What is the difference between the purple and the blue? The purple and the blue get really close to 0. And the red does not get really close to 0. So the red is always going down. The purple and the blue are also always going down. But the red kind of bottoms out at some non-zero amount. In this case, I guess something between 0 and 2. Where the purple and the blue, they bottom out at 0. So this is the next question. So question 2. If we keep collecting data, will the error get closer and closer to 0? Answer. What's the answer? So if you selected purple or blue, you think it goes down to 0. If you selected red, you think it just gets closer and closer to this special dotted line. What do you guys think?
We have irreducible errors, so never can be.
Okay, yeah. So you're on the side of will it ever get closer to 0? You're on the side of no. Okay, and then what is your reasoning? Why do you think it?
Because we have irreducible error.
No, because of the irreducible error. Very nice answer. Because of the irreducible error. That's a wonderful, short, perfectly correct answer. And this is exactly right. So I think this is another common misconception in data science or statistics, is that if you collect enough data, then your error will get down to 0. The answer is no, it will not. The correct answer is the red graph, which is steadily decreasing but does not reach 0. And the reason it does not reach 0, the amount it reaches, is exactly what we did in the previous problem, is the irreducible error. So if we have enough data, we sort of learn the dice perfectly well, and we can figure out what would happen if we knew the dice, but we will never get down to a situation where we have 0 error. That would be too much to ask for. The dice always has some amount of error. And I'm going to go back and fill in when I started the class on my little thing over here. We're going to figure out the formula for the error, but let's give it a name first, which is, in addition to the error that we had before, there's going to be some new source of error, which is the error due to limited data. So before we learned about the irreducible error, and now there's an extra source of error. There's extra error due to limited data. So if you know all the sides of the dice perfectly well, there's this irreducible error. If you don't know the sides of the dice perfectly well, you have an extra source of error due to this limited data, and this is called epistemic error. Epistemic. I have to spell it correctly. It's a fancy word. Okay, let's give it a try. Whoa, that's not what I want. This one. Okay, And epistemology is the philosophy of knowledge, and epistemic means this error is due to our lack of knowledge. If only we knew things better, we would have less error. We would not have this epistemic error. But no matter what, we're going to have the aleatoric error. That will never go away. So there's two types of error. There's the error from the actual uncertainty of the dice roll, and then there's the error because we don't know everything, right? Where we don't have perfect knowledge, that creates some error, and then the dice are random, that creates some more error, and the two errors add together. So indeed, in this graph, if you chose the blue curve is the graph of just the error due to uncertainty. Just the error due to our knowledge. So the epistemic error does go down to 0, but you will always have some extra amount of aleatoric error due to the dice roll. So there's sort of two sources of error. We're going to mathematically analyze it, and you'll see the two sources of error come out mathematically as well, but that is how I think about it. Okay, let me put this one back up. Any questions or comments about this way of thinking or the thing we're about to show? We're about to find the formula in 1 second, and then it'll also be clear. Okay, let's do the formula. And so here's the formula. We're going to do some calculations. So, and to start with, so we're going to set a y hat equals 1 over n times y1 plus dot 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 plus yn, the sum of the first n things, and then divide by n to take the average. And then so the loss function of this y hat, what is it? Well, it's the average of y hat minus y squared. So just like before, here again, capital Y is our test. Y, this is our test. Y equals the test point. The test point. Right? So we have our training examples. Maybe I should label these as well. Y1 to yn these are training data. Training data. It's called training because we used it to come up with our estimate, right? So we combined the things in our data set to get our estimate, y hat, and then we were testing to see how well we did based on a test point that we haven't seen yet. And we're looking at the average. So this is the theoretical average loss. The theoretical average loss. Square loss. Okay, same setup as before. And now we're in an advantage here. We could do a lot of lines of algebra to simplify this, but we just did that. And if you simplify it, what you will get is this is equal to, after all the algebra from before, this is equal to y hat minus the expected value of y, the true average squared, plus the variance of y. That's exactly what we showed a minute ago on the situation where we perfectly knew the dice. And in this case, y hat is this number. So I can just plug that in as a thing. So this is 1 over n times y1 plus dot 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 plus yn minus the true average squared plus the variance. Okay, so this is the empirical average. Empirical average. And this thing is the theoretical average. Okay, so this is this kind of decomposition. When we roll the dice, the empirical average, the actual average of the data points we saw, will not match the theoretical average perfectly. It will be off by a little bit. And that term, however off we are, we square it, and we add that onto the variance. This term is our lack of knowledge, right? If we had an infinite sample size, then this and minus that would go to 0. That is the kind of thing you learn in probability class. So, this is the extra error. This altogether, this difference squared, this is the extra error due to data that I called the epistemic uncertainty. Okay, we're gonna analyze it in just 1 second. Right, this variance, this is the irreducible error that we had before. This is the error from before. I'll say the irreducible error from before. Okay, and so it really does add, right? It's a sum of this extra error plus the irreducible error, and that is our loss. So this is the loss of this estimator. Okay, very nice. So the question that you might be interested in is, Okay, so for a given y1 to yn, this tells you how far away you are. But how much is it on average? So far we've averaged over the test data, but could we average over the training data as well? So we can make a new loss function. We can say, what is the average averaging over y1 to yn, y1 to yn of the loss? Okay, and what this is saying, this is the average loss of a sample size, the average loss for a sample size n. So in other words, instead of doing this whole calculation after we have rolled the dice y1 to yn, we could say, on average, if I'm going to do an experiment where I have 100 dice, how big should I expect the error to be? And that's the average over the training set. So this is the average loss for a given sample size, whereas before we were doing the average square loss for a given y1 to yn. Yeah, I'll add that back in for given y1 to yn. And that's the difference between the two calculations. I'm just going to literally take what I had before, and I'm going to put a big expected value in front of everything. So it's the expected value over y1 to yn of the calculation from before. Minus the expected value of y squared plus the variance. Okay. So how big is this thing on average is sort of the question of, on average, how far is the empirical average away from the theoretical average, right? And if you know some probability class, you might have seen results. So the law of large numbers tells you that in the limit as n goes to infinity, this difference should go to 0. So we should get something that as n gets bigger and bigger is going down to 0. That's the law of large numbers. If you've seen something called the central limit theorem, the central limit theorem tells you exactly what is the distribution of the empirical average minus the theoretical average. We just need to know how big is it when you take the expected value, so it's actually a very simple calculation. So we're going to see that in just 1 second. There's a lot of moving parts here, a lot of stuff flying around the board. This is a great place to pause. Any questions or comments about the setup here before I launch into yet another calculation? Okay, let's launch into the calculation. The first thing to observe is the variance of y. That's a number. That'll just get pulled out. So the variance, that is very easy to do. So let's do it this way. So this is equal to this expected value over the data points. I'm not going to write y1 to yn just to save space. And then I have this big bracket 1 over n y1 plus dot 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 plus yn minus the expected value of y all squared, and then plus the variance. So that's nice. Okay. Okay, that's a nice thing. And then I have a 1 over n, and then I square it. Why don't I pull that out? That'll cost me, it'll get squared on its way out, but that's perfectly fine. So why don't I just move this back up and make this a 1 over n squared, and then I gotta delete this 1 over n, and then also I gotta multiply this guy by n. Let's sneak an n in here. Minus n times the expected value. Okay, so hopefully that's the same. If you were to factor the 1 over n squared in, you would get a 1 over n here, and then the n would kill the n over there. So it's the sum y1 plus dot 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 plus yn minus n times the expected value of y, all squared. And now, something we did earlier in the class will help us. So we need a way to simplify. It's the expected value of something squared. How can we simplify the expected value of something squared? Let's scroll up and see. What tools did we have earlier in the class that would help us? Oh, here's the expected value of something squared. And this says, if you have the expected value of something squared, you can break it up into little pieces where the things are the things that you're adding up. Okay, do we have a situation like that over here? We're adding up the pieces by 1 to yn. Okay, but actually, there's two things that are annoying. One is this, I don't know what to do with this minus n. That's annoying. And then the second thing that's annoying is the things have to be uncorrelated. So when you add up the pieces, like adding up y1 and y2 and all the way up to yn, the pieces are supposed to be uncorrelated. The expected value of the product of these things should be 0. and they're not. But fortunately for us, it's like a two birds with one stone situation. What if I take this minus n and I feed it into here? Then it will simplify quite nicely. So let's do that. So this is 1 over n squared, and then the expected value. And instead of writing y1 plus y2 plus dot 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 all up to yn, and then subtracting n times the expected value of y, I'm just going to write it like this. It's y1 minus the expected value of y plus y2 minus the expected value of y plus dot 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 plus yn minus the expected value of y. All that gets added together and then squared. And then we finish the expected value, and then we add on the variance from before. So in other words, instead of adding up n things and subtracting n times the constant, why don't you subtract the constant from each term individually? That was perfectly good. And now we can use the Pythagorean theorem for random variables, because each of these things is now mean 0. What is the average of y1 minus its average? 0. What is the average of y2 minus its average? 0. So all of these things are mean 0. By independence of y1 and y2, they are uncorrelated. So these are uncorrelated. Actually, they are independent. So I'll say each term is independent and mean 0. 0 on average. So because each term is mean 0 and they're independent, they are definitely uncorrelated. If we do the expected value of the product of any two terms, it'll be 0 times 0. And so we can use Pythagoras. So by Pythagoras, we get, so by Pythagoras, one over n squared, and then it's going to be a big sum of individual things squared. So y1 minus the expected value of y all squared plus dot 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 plus yn minus the expected value of y all squared plus the variance. Okay. So in other words, we've taken this complicated thing, which is a sum of a bunch of stuff all squared, and by Pythagoras, we can add up the individual parts. That's what Pythagoras lets us do. This is the Pythagoras theorem with n things, not just with two things, but that is perfectly fine. Okay, we're very close now. We just have to observe that there's already a name for this number. This number looks very complicated, but it already has a name. Does anyone know what is the name of this funny combination? Someone said something? What is it? The loss? It is the loss of something, but what specifically? Like it has a. I would say this is the loss of rolling one dice. But there's a sort of a name for that. Yeah.
Is it the standard deviation?
It's very close to the standard deviation. The standard deviation of some random variable y. That's the definition is the square root of the variance. So if there was a square root, then it would be exactly the standard deviation, but there is no square root. So what is it? It's the variance. It's the variance. This is the variance of y. Our old friend, the variance of y. And in fact, this term is exactly how this guy appeared. So when we did the calculation earlier, this variance appeared from this kind of thing. So what is going on here? We have 1 over n squared, and then we have the variance n times. So we have 1 over n squared, and then we have the variance of y plus the variance of y plus dot 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 plus the variance of y. 1 for each dice roll. y1, y2, y3, they're all the variance of y. How far away are they from the mean? They're the variance of y. And then plus the variance of y. Okay, and this is a nice little calculation. There's a 1 over n squared, and you're adding up the same number n times. So that's 1 over n squared times n times the variance of y plus the variance of y from before. Let me put that one over here. Okay, and now there's a nice simplification. 1 over n squared times n is a 1 over n. So 1 over n times the variance of y plus the variance of y. And this really is the decomposition I promised you. The variance of y, this is the aleatoric irreducible error. And this is the epistemic error. And you see it has a 1 over n. Okay, so the more dice you roll, the smaller this error is. If you roll 100 dice, then this is a 1 over 100, very teeny tiny number. If you only roll 5 dice, it's 1 over 5, and then maybe it's pretty big, right? And you can compare it. It's always less than this amount. So sort of the randomness inherent to the dice is like a bigger problem than the randomness from your uncertainty. This one will go down to 0. What does the graph of 1 over x look like? It's exactly what you saw, right? So this is n versus error. And it goes down to 0. So this one, the epistemic error goes down to 0. The aleatoric error is always constant. And so the total error, right, the total is exactly what was in that red curve. It goes down like this. So this was the function 1 over n. And then this is the function, let's put 1 plus 1 over n times the variance. Okay, and this is n on the x-axis. Getting really, really close to just the variance over here. This is 1 over n times the variance. That one goes to 0. Okay.
Sorry.
Yeah.
Why is the y minus expected? Y equals to
Why is it? Why is it true that this one equals the variance?
Yeah.
So the definition of the variance is you subtract off the mean, you square it, and you see how big it is on average. So this is the definition, I guess, if you want it. The variance of some random variable a is the expected value of, what is it? Something minus something squared. What is the something? A minus expected value of a, all squared.
I mean, I can't decide. I thought it's like I didn't know, like so many expected.
Okay, yeah, that's true. There are many expected values, right? There's an expected value on the outside, and then there's an expected value on the inside as well, where you subtract. There's 2. Yeah, it's a good point. Okay, so what is the moral of the story? Is I wanted to show you, so if we did the example that only had the aleatoric. That was the only error. So if you know the sides of the dice, you just have this error. If you don't know the sides of the dice and you're estimating using data, now you have 2 sources of error, okay? Very nice, really good to understand these 2 different things, right? I think the biggest misunderstanding is people forget about this one. So people think the error, as you increase the sample size, you go down to 0. You don't go down to 0, you go down to whatever that is. That's a really important thing. So the total looks like this. Okay, I guess we can go fill in our table now. So the answer is this big question mark. And the answer is 1 plus 1 over n times the variance. Okay. All right. We're about to start. We're going to start this next one, which is they talked about it in the videos, and I have an extra video on this thing. And this is going to be our first one where we have x values as well. So far we've only had y values, and we have done this decomposition of the error due to estimating y values. But now we're not estimating just a y value. We have to estimate a whole function. So we must estimate a whole function. So we're doing find f hat of x, right? So you don't want to know what is the y value. You want to know for a given x value, what is the thing? And there's a function f hat that you're trying to estimate. That's what we're going to do. Okay, wait. Before I do that, we're about to launch into this. And we're going to learn about bias variance decomposition and underfitting and overfitting. It's definitely going to take us into our next class. But any questions or comments about any of this stuff on the board so far? Okay, let me show you the example. So we're going to do an example where there's x's and y's. And I'm going to tell you how we're going to measure our uncertainty. Okay, so now here is the example. So we are given a bunch of xy pairs. So we're given x1, y1, x2, y2, xn, yn, right? So we're given x's and y's. And our goal, what we want, find f hat. So f hat of x. And we would like f hat of x to be really close to y. How do we measure how close we are? We use the square error again to minimize square error. So what is our loss? The loss function now is a function of f hat. Right? Before, the loss function inputted y hat, our best estimate. Now the loss function is inputting f hat, our best estimate of what the function is doing. And what is the loss of f hat? Well, it should be how far away is f hat of x minus y all squared, right? So we're sort of replacing the y hat from before with an f hat, and now the average is over a test point x comma y. So how far away are we on average? So all of the things we did before, we're sort of just adding a dimension of this x, right? There was no x before, now there will be an x. You can sort of think of this as like, imagine I roll a dice and I tell you the x value tells you the color of the dice. Is it a red dice? Is it a blue dice? And maybe the dice are all slightly different. So you can sort of take what we did before and think of it as now we have extra knowledge, these x's, and we're going to have to use that to figure out what's going on. Let me show you the problem I have set up for us, the example. And I call this one, I think about this as the cannonball distance estimation problem. So the x value I think of as an angle in degrees. So you can be either 0 degrees or 90 degrees. And you should imagine we have a cannon, we set it to the angle, and then we press fire, and then we see how far the cannonball goes. And sometimes it goes really far, like over here it went 15 meters. That's pretty far. But sometimes it goes backwards. So here it went like -5 meters. And what we're trying to figure out is, on average, how would we figure out how far the cannon shoots on average? That's the f hat that we want. So I guess maybe the thing that is I haven't said yet is that we will assume that there is a true answer. So assume the truth is y equals some real f of x plus epsilon, where epsilon is some error that is not depending on x, all the other stuff. And in fact, we know the best possible estimate from our work before, the best possible estimate would be this true thing. And you can also write it like this. It's the expected value of y given x equals x. So this thing over here, let me relabel things a bit. So the true value of f is this thing, f of x. And the best possible estimate is f of x, f hat equals f. Best estimate is. Okay. What is this thing? This is the conditional expectation. So given the x value, what is the average of the y's? That is like saying, if you know what type it is, then the best estimate is the average. This is what we proved before. So like the reason this is the best estimate follows exactly from the kind of logic we did before. I will show you what this looks like in the cannonball problem. Are you guys ready? In the cannonball problem, the unknown true function is this blue function over here. So this is the f. And on average, when you shoot a cannon at 45 degrees, on average, it will go 10 meters. That is what the blue is telling us, right? Of course, when we did our observation, it didn't go 10 meters because there was extra noise. So this is how we're thinking about real life. There's this unknown blue function that is telling us the true average of what's going on. And the points we observe are kind of above and below the true average. And we would like to estimate, we would like to get really close to this blue function. That would be our best possible. If we could somehow come up with exactly this blue function, that's the best we can possibly do. All right, questions or comments about the setup so far? So we got the data, we got the blue. Of course, in real life, you don't know the blue. You will never know the blue in real life. So I'm gonna cover up the blue. You should just know it's there, but we don't have access to it, right? We gotta come up with, just using the data, come up with our best estimate. Okay. Okay, we want to get close to the blue. And in fact, okay, let me write down one more thing. We can show that the loss of some estimator f hat is essentially, it's f hat of x minus f of x all squared plus the variance of y. Okay, and this is true except for this is given a certain x value, but the x value is random. So we actually have to average this over all the x. But like morally speaking, think of it like this. I'll put an x value like this, and it's the variance of y given x. So in general, you want to be as close to the true function f as you can, measured by the square. You want to get as close as you can by the square. That's what we're trying to do. All right, here is the method we are going to use. Our method. And we're going to do lots on this next class. Method, and I call this the local averaging. They also mentioned this in the videos. So if you saw the videos, which you should have, you will have understanding this local averaging. And the idea is to average nearby values. Average nearby values. Call them nearby y values. So what do I mean by this? Let me show you in the picture. So we'll go back here. Okay, so let's pretend we want to come up with an estimate at some point. And I have a little test thing for this. So what I'm going to do is let's pretend I want to figure out what should our estimate be at 30 degrees. So I take this little thing and I do it at 30 degrees. And then what I do is I set a window size. And I can make the window size, I can make it really small or I can make it really big. I can do either one. Let's set it to, I guess, 15. That's a nice round number. So here I'm estimating the value at x equals 30 by using a window size of size 15. And what do? I take all the cannonball shots that are within this window. So there's that one, this one, this one, that one, this one, that one, this one, and that one, and I average them. So I take the average of all these y values and I get this point over here. And then I say, when you shoot the cannon at 30 degrees, based on the data that I have, I think it's going to be just over 7. It's going to go 7 meters. And I got that 7 because I'm averaging all the cannonball shots in my data set. And this is, again, like the thing we want is the sort of true average, and this is a kind of empirical average. Right? So this is the same kind of thing we did before. You want the true average. You have data. What do? You make the empirical average, and you cross your fingers and hope that they're close. But there is one thing in this problem that did not exist in the dice before, and that is the thing that makes the problem a million times harder and a million times more interesting, which is how big should the window be? You see, because I could do a really small window like this. I could do a really big window like that. What is better? Should I do a small window or a big window? Maybe if I go to a point like this, maybe you'll get some sense of it. Is a big window better or a small window better? Which one's better? That's the question. And that did not exist before, right? Before there were no x values. There was no notion of window size or closeness on the x-axis. And now that we've introduced an x-axis, the problem is like sort of infinitely harder. And the question is, we're going to start with, is window size small better? Is window size big better? That will be our last mathematized question for today. And then we will take that as our starting point next class. Which window size? So in the nearby neighbor averaging, is it better to have a window size? I call the window size delta. Delta stands for difference. It is the width of the window. It is the difference between the point you are averaging and the point you are. So is it better to be very small or is it better to be very big? Okay, and then there's some reminder about thinking logically about smalls and bigs, but I will let you select one of the three options. Let me give you let's say a minute to think about that. Okay, 30 seconds left. Put in your guesses as whatever you think it is, whichever way you're leaning. I don't think you have time to fully figure it out and fully work through it, but just tell me what you think based on what you know. Okay, 5 seconds. Okay, what did people say? Reveal counts. Okay. So only one person said smaller is better. 5 people said bigger is better. I will say, it's very tempting to think bigger is better based on this little reminder that I wrote, which is I said small windows contain very few data points, but big windows will contain many more data points. And if you remember, earlier in the lecture, we had this idea of more data is better, right? We did this whole calculation, and we said the epistemic error goes down like 1 over n. So maybe you want as many points as you can. You want to make n as big as possible so you have the smallest amount of epistemic error, right? Bigger sample sizes are better. Big windows have big sample sizes. So should a bigger window be better then? That's a very tempting idea. You guys all must have seen the videos because you know the answer is secret third option. And this is, I think, the most confusing thing when you're first starting out in data science is this kind of thing, is that sometimes you don't want the biggest possible sample size, right? So earlier I wrote this very cryptic all else being equal. So all else being equal is more data ever worse. All else being equal, you want as much data as possible. But the problem is in real life, all else is not equal. And so we're going to see that as you make the window size bigger, you are getting more data and you are decreasing your epistemic error, but you are increasing something else. So this is the big idea we are going to tackle next time. So the big idea, this is a really important idea. Big idea is that bigger sample size, e.g. big windows, give up something else. Give up. Mystery thing. All right, mystery thing. And in real life, what you have to do is you have to balance the mystery thing with the bigger sample size. So in addition to our aleatoric error and our epistemic error, we're going to have to balance out this mystery thing. And we're going to see that next class. Maybe I'll spoil it. The mystery thing is something related to bias. Okay, we're going to see that next class. Okay. Any questions or comments before we go? Yeah.
What was the variance that we were talking about just a little bit?
Yes.
Yeah. Why is that our variance?
Yes. Okay, this is a point. So what's written over here in tiny writing is the variance given the x value. And what this is saying is, in our picture over here, let me put on the real true function. Let me take this thing off. So this is the average, and the points are above and below the average line. So you should sort of think of these points as being equal to the average plus some random noise. And that random noise has some amount of variance, but the variance could depend on the x value. So it could be that when you shoot the cannon at 0 degrees, there's very little noise, and when you shoot the cannon at 45 degrees, there's a lot of noise. And that's what the variance meant. It's the variance of the y values given the x values. So it could be more or less depending on the x. And at the end, we average over all the possible x values. Maybe I could write that a little bit more clearly. That was a fantastic question. So this is the variance of y. I think I wrote it as x given x equals x, but let's just write given x. So that is what this means. And I think I can, if I move this thing up to the top or the other side, then I'll have a little more room. Okay. X, the variance of y given x. Yeah. Okay. And the idea is, in general, y can have more or less variance depending on x. In a lot of situations, it is fixed. In particular, the example I did on the board, in Desmos, it's always a constant amount. But in principle, you need to average over. Yeah, great question. All right, any other questions or comments? Okay, we're going to see you on Wednesday then, and we're going to continue this cannonball thing, and we're going to try to find a way to balance the window size that is not too big or not too small, but that Goldilocks would really like. Okay, see you on Wednesday.